Hello, I'm Akhilesh Kumar Srivastava and I'm going to discuss today the binary search trees. We should first discuss about the array-based searching techniques and its limitation, and then we will come to the binary search trees. So we have some of the array-based searching techniques, and considering that the searching is a very frequently used techniques in the computer science applications, we have some of these techniques known as linear search, and this is also known as the sequential search. Another one is the binary search and the index sequential search. The linear or the sequential search requires order of n time for the search operations. The binary search requires order of log n time for the search operations. It's a technique which is known as the decrease and conquer. It's based on this approach. The linear or the sequential search was based on the brute force approach. It requires the maximum time for the searching. Based on the decrease and conquer approach, we have another technique known as the index sequential search. It requires the time of order of log n upon I, where we are considering that every ith element is maintained in the index. All these techniques, all these array-based searching techniques, linear search, binary search and index sequential search, perform the searches in good time. But if we consider that along with the searching, if insertion and the deletion operations are also carried out frequently, then these algorithms do fail. The fail means they require order of n shifting operations. For insertion they require order of n shifting, and for deletion also they require order of n shifting. So based on this demerit of the array-based searching techniques, we can consider the binary search tree. We can consider that our data elements are stored in the form of the binary search tree. In the binary search trees are a special type of the binary trees in which the elements are stored such that every element towards the left of any node contains less information than that node, and every element towards the right of that node contains more information than that node. In other way, we can say, if we say that this is a binary tree, in that case this represents the root node. Every element coming towards the left subtree of the root node contains less information, and every element coming towards the right subtree of this node contains more information. In this binary search tree, let's say 100 is the root node, 100 is the key value of the root node, 50 is coming towards the left, that's why it's containing less information than the root node. If we consider this as a root, then 30 is coming towards the left of this node, that's why it's containing less information. And since 90 is coming towards the right of this node, it is containing more information than 50. But please see that 90 is more than 50, but it is less than 100 because it is coming towards the left subtree of 100. Similarly, on the right side, you can see that 150 is more than 100 just because it is coming towards the right of 100. 120 is less than 150 because it is towards the left of 150. But 120 is greater than 100 because it is coming towards the right subtree of this node. So this is the binary search tree, and if we have constructed the binary search tree, a check can be applied to see if the constructed binary tree is correct or not. We can perform the in-order traversal, and in-order traversal of this tree will give us the number in the ascending sequence. That means if we perform the in-order traversal on this tree, this will result us in 30, 50, 90, 100, 120, 150 and 170. That means if we are constructing the binary search tree, after constructing the binary search tree, we can apply a simple check operation by carrying out the in-order traversal, and it will result us in the ascending sequence of the numbers. There are some of the very frequent operations applied on the binary search tree. We will discuss today those operations. Since we have constructed this binary search tree for the search operations only, so the very first operation we will discuss today will be the search on the binary search tree. Another one we will discuss is how to find the minimum element from the binary search tree, how to find the maximum element from the binary search tree. Then we will discuss about insertion operations in the binary search tree, and then we will discuss about the deletion operation in the binary search tree. Starting with the search operation, let us take a binary search tree. Suppose we want to find out an element, we want to search an element X in this binary search tree. For every search operation, we will have to start from the root node. Now the root node will guide us either to go towards the left or the right, depending on what is the value of the current node and comparing the value of that current node with the search key. For example, if you are going to search about 30, in that case 30 gets compared with the information of the root node. Since 30 is less than the root node, it will guide us to go towards the left. Now 30 is less than the value of this node, so it will guide us to go towards the left. Now since 30 is greater than this node, then it will guide us to go towards the right, and incidentally the information of this node is equal to the searching value or the search key. It will return the pointer to this node. So this way we can carry out the search operations. Starting from the root node will guide us towards the left or to go towards the left or the right, depending on what is the information of the current node and what is the information of this search key. Now let us write this search operation in the form of the algorithm. This is the short form of the binary search tree BST, and the search operation we are carrying out. Suppose tree is a pointer to the root node and X is the search key that we are interested in finding out. For searching, we will traverse the binary search tree and we will traverse till we reach the leaf node. So for traversing, let's take another pointer P, which is at the root node. We are considering that tree is the pointer to the root node. We are taking P also to point at the root node. By this assignment, P equals to tree. Now according to the traversal, while P doesn't become null, we will traverse and we will compare the information of the search key with the information of the current node. If the information of the search key is equal to the information of the current node, it will return the pointer to that node. But if there is no match, in that case we shall either go towards the left or towards the right. So if the search key is less than the information of the current node, we will go towards the left, and if the search key is greater than the key value of the current node, we will go towards the right. So this way we can either go towards the left or right until we find that the search key is equal to the information of the current node. If the search is successful, the pointer to the node will be returned from this statement and inside this while loop. And if we come out of this loop, in that case the element will not be there in the binary search tree. So since the element is not found in the binary search tree, we will return null. So this is the search operation, and since this search operation, in this search operation we are either going towards the left or towards the right, we are picking a unique path for this search operation. So we can go from root node to any of the leaf node. That means from root node to the depth of the tree. If we consider that we have n elements in the tree, then the maximum depth of the tree is expected to be log n. So the search operation will be carried out in order of log n time. Let us see the another operation, which is minimum. Minimum is actually finding out the pointer to the node that is containing the minimum information. Pointer to the node, we are not interested in finding out the key value of that node, but we are interested in finding out what is the pointer to the node that will contain the minimum information. So naturally, since less informations are found towards the left of the tree, so extreme left element will be the minimum element. So let us write the binary search tree minimum operation. Let's again say tree is the pointer to the root node. We will traverse the tree towards the extreme left, and the extreme left element will be the desired element, and we will return the pointer to that node. So we are taking P equals to tree. Wherever tree is, we take P there. Now extreme left, for the extreme left element, left of that will be null. So while left of P is not null, we go towards the left. The moment left of P becomes null, it means there is no left element to that node. In that case, we will return the pointer to that node, saying that this is the node containing the minimum information. For example, in this case, this is the node, its left exists, so we will go towards the left. Now the left of this also exists, so we will go towards the left. Since the left of this does not exist, we stop there and return the pointer to this node. So this P is actually pointer to the minimum node in the binary search tree. Similarly, we can find out the maximum also. In the maximum operation, we will start from the root node. Since maximum element or the larger element can be found towards the right only, so the tree will guide us to right, go to the right, go to the right, go to the extreme right, and the element on the extreme right will be the maximum information. So in this algorithm, we just change left to right and it becomes the maximum algorithm. Now let us discuss the insertion operation in the binary search tree. We are considering that the insertion and the deletion operations are also very frequent, and that's why we have switched from the array-based searching techniques to the tree-based searching techniques. So let us discuss the insertion operation. In the insertion operation, once again the pointer to the root node is given. There is some X information which is to be inserted. And for carrying out this, we will have to traverse the tree to find out what will be the appropriate position of X. Where should it get inserted? So for that, we will once again have to check the information of the current node with X value. And if the information of the X is less than the current node's information, we will go towards the left or we will go towards the right. And please remember that every insertion operation takes place only as a leaf node. Every insertion operation will take place as a leaf node. Considering we have, let's take an example of this binary search tree. Suppose this is a binary search tree and we want to insert 45 in this binary search tree. So for insertion of 45 in this binary search tree, we will start from the root node. We will see if this 45 is less than 100, we will go towards the left. Since this 45 is less than this node, we will go towards the left. Since this 45 is greater than 40, we will insert 45 towards the right of this node. Fine. So let's say this pointer is tree, means the root node pointer is tree. From our side, we take P to point at the root node itself. And for writing this operation, let us take another pointer that is Q, and Q is always the father of P. When we traverse this tree, we downshift the Q also. Along with P, P will move either towards the left or the right, but Q will always remain the father of the P. If P remains here, Q will be here. If P remains here, Q will be here. So now let us write this algorithm, and before that, let's say once again we have to insert 45. So P equals to tree and Q equals to null, meaning that Q is taken as the father of P, and we are going to traverse this tree till P becomes null. So by the time P is not null, our traversal will continue. So if X is less than the data element of P, we will move towards the left. And if the X is greater than information of P, we will move towards the right. Now, whether we are going towards the left or towards the right, we have to downshift the Q also. So we make Q as P. By this way, Q will always remain the father of P. Now once this operation gets completed while P is not null, it means when P becomes null, we will come out of this loop. So Q will be here. In this case, Q will be here because the P has become null. If P was here, Q was here. When we have downshifted P, P has come here, Q was here. When we once again downshift P and Q, P becomes null and Q comes here. So So when P has become null, we either have to insert the elements towards the left of Q or towards the right of Q. So we will have to apply a check here. If X is less than information of Q, then we will set left X towards we will set X as a left child of Q. So this is carried out by the operation set left. Otherwise, it means X is greater than information of Q. In that case, we will perform the set right operation. So set left and set right operations are considered to be the standard operations, and it is only used for insertion of a node as a left child of any node, and for set right, the node is inserted as a right child of the given node. So this is the insertion operation in the binary search tree. Now let us discuss the deletion operation on the binary search tree. Before going to the deletion, there is one more operation which is known as successor of the binary search tree. Let's say there is an operation known as BST successor P. Here BST successor P means we need to find out the pointer to the node which is containing immediate higher information than this P node. So by the methods we can see that since higher informations are found towards the right of any node, so minimum of the right will give us the successor of the given node. So let us say that BST successor is a standard operation, and we can find out the successor of that node by the use of this operation. For the deletion, we have three cases. In the binary search tree, if the given node which is to be deleted is having only one child or zero child or two child. Suppose we want to delete this element. So this element does not have any child. If we want to delete this node, in that case, we will simply delete this node and we will find out if this node is the left child of its parent or right child of its parent. If it is the left child of its parent, we will set the left of its parent as null because this element will be deleted. There will be no element towards the left of 90. That's why we have said that the null, we will set the left child of its parent as null. Now this case 2 says that if we have only one child, so let's say this is the case where we have to delete 120. 120 has only one child. So for deletion of 120, we need to set two pointers. For deletion of this, we will bring this 110 at the position of this, and then we will have to find out if this 120 was left child of its parent or right child of its parent. If 120 is the right child of its parent, in that case, we will set right of its parent to this node and father of this node to the father of this node earlier. So now we need to make these two adjustments for the deletion by case 2, which is that the node which is to be deleted has one child. If we want to delete a node which is having two children, in that case, we need to make use of this successor. For example, suppose we have to delete 100. If we have to delete 100, it has both the childs, this one and this one. Now for deletion of this node, we will have to find out the successor of this node. And successor of this node, logical successor of this node is this node. So for deletion of this node, we will delete this node and we will bring this node here, the key value here. It means for deletion of any node having two children, we will first have to find out the successor, and then we will delete that successor either by case 1 or case 2, and then we will bring this information, the key value of this successor, at the position of the deleted element. So these are the three cases of the deletion, and all the algorithms that we have discussed today, the search, minimum, maximum, insertion and deletion, all these operations are carried out in the way that we move from the root to either of the path which is leading towards the leaf node. And since the path is leading from the root node to the leaf node, any of the operations can go only up to depth. And we have already considered that the depth of the binary search tree is order of log n. Hence, the complexity of any of these algorithms will be at most order of log n. Thank you.